All right, let's get started. So hope all of you guys had a good break. Welcome back to the last week of classes. We are in the home stretch. So there are just a few more things that we wanted to tell you about for the course. So we're going to start today. Basically, we're going to do today a bunch more ideas for classification problems that we didn't cover earlier. You can think of it as sort of the advanced classification primer. So there's a whole bunch of new ideas here, and there's a huge literature on each one of them, but hopefully this will get you a good overview. So let's get started. So you remember, hopefully, the naive Bayes algorithm. So there was this graphical model here where we had the class variable y and a bunch of features x of each instance, and the idea was that you would observe all of the x's, and then that would let you infer the y, right? And you all remember this plate notation. That means that there are k different features that you observe for each example, and there are n different training examples. Each one has a y and k of these x's, right? And in particular, the arrow in the Bayes net was this way, right? And it implied that every one of these observed features was conditionally independent given the class variable, right? And that was how we did the inference. If we worked it all out, right, we had a model like this, that the joint probability of the x's and the y's was the product of the probability of the y's and the conditional probability of each of the x's given the y, right? And the point of this factorization, right, this factorization into a bunch of separate conditional probabilities for each x was what encoded the conditional independence assumption. And the model had, well, 2k plus 1 parameters, right? There was the probability of the y's, and then conditional on minus or plus, you had a separate probability for each one of the x's. Okay? And the way we fit it was by maximum likelihood estimation, right? And maximum likelihood estimation for this model turned out to be particularly simple. You'd just, to get the probability of y being positive, you'd count the number of positives and divide it by the number of training examples. And then to get each one of these probabilities, you'd specialize to, whoops, this should be a plus here. There, I can hardly tell the difference between my having gotten it right in the slide. So you'd split it into those where the y's were negative and the y's were positive, and within that set, you would count the number of times the x was 1, and the same thing, the number of times the x was 1 within that set, right? And then when we worked it all out, the conditional probability of y being positive given the x's took a particular form, right? It was a logistic function, 1 over 1 plus e to the minus z, where z was a linear function of the x's, right? So you would calculate the w0 and the wj. They came from these parameters here. So maybe there weren't actually 2k plus 1 independent parameters that matter, right? Because you combine them into only k plus 1. And then you use those to calculate a linear function of your examples, and then you put that through this logistic squashing function that looked like that, right? So this all sounds familiar to everybody? Yes, good. Okay. And then, so given that form, so I'm going to take this expression and put it up at the top of this next slide, right? This is the same expression here. So we know what the expression for p of y given x's is, and so maximum likelihood tells us that we should maximize the likelihood, right? Which is argmax of the product of all of the probabilities of the y's given the x's. And if you plug in this form, right, you get argmin over w, so you get, right, a negative here because of the 1 over, and then log of 1 plus x minus zi, right? And then to handle both positives and negatives, you have yi times zi, right? Plus 1 or minus 1, so that you're always, you always want to have this expression be big, right? And then so we did the argmin of the sum over all training examples of this function of yi times zi, where the function looked kind of like this, right? It was linear over here, and then it had a curved segment, and it turned linear over there, right? So this all sounds familiar as well, right? And so the puzzle that I want to give you is we used maximum likelihood on this page, and we used maximum likelihood on the previous page, and yet we got to a very different looking answer. So anybody have a thought for what the difference is? Yeah. I'll bet it does have something to do with discriminative versus generative models. You were reading behind, right, as opposed to ahead. Okay, you've given it away. The answer is, in fact, the difference between discriminative and generative models. And the difference was I said maximum likelihood twice, but what I did was slightly different, right? I maximized the joint probability of x and y on the first slide, right? That gave us naive Bayes. And then I maximized the conditional probability of the label given the inputs, and that gave me logistic regression, right? And this sort of maximizing a conditional probability, right? This is called maximum conditional likelihood to distinguish it from original maximum likelihood, which really refers to this, maximizing the whole joint probability of everything you've seen, right? And another word for this is a generative model, because this is talking about the full distribution. If you have a model of this distribution, you can sample from the joint distribution of x's and y's. This is a discriminative model, right? It doesn't give you enough information to sample x's and y's. Right? It just gives you p of y given x. So if you had an x, you could sample to y, but you don't know how to sample x, right? And so these two things, they both sound reasonable to do, and they both give you good classifiers, and either one can perform better than the other. And so how do you pick? Well, so the conventional wisdom is that logistic regression or maximum conditional likelihood, a discriminative model, is going to be better if you have tons and tons of data, and naive Bayes is going to be better if you have only a very little data. And we'll see why that is in a couple of slides. Okay. Oh, and I should point out also, so there's not just two answers, right? We also told you about, right, the support vector machine, which had essentially the same optimization problem, but with a piecewise linear function. And so you can think of support vector machines as being like logistic regression. They're a discriminative model. And I usually think of, there are plenty of arguments for why support vector machines should work, but one good one is that they're approximating maximum conditional likelihood. All right, so we have all of these different ways, and I don't know about you, but it disturbs me at least a little bit that there's all of these different prescriptions that lead to different answers. You had a question? No. Okay, so all of these different prescriptions that lead to different answers. So it turns out, though, that all is not lost in the sense that they're actually not different prescriptions. You can think of them as both being, there's maximum conditional likelihood being just an example of maximum likelihood, which is kind of cool. So right here we have maximum likelihood and maximum conditional likelihood. And what I'm going to say is that basically this maximum likelihood is the basic principle. And maximum conditional likelihood is just an example of it. So the way that works, suppose that we write this probability, right, this one right here, as follows. Suppose p of xi, yi given theta is equal to, sorry, I'm going to write this one here in a way that involves this one, right? So I start off with the probability of xi given theta, and then multiply that by the probability of yi given xi and theta, right? And this is always safe to do, right? Because this is just an application of Bayes' rule. And so now I'm going to make an assumption that this is equal to p of xi given theta x times p of yi given theta y, right? And so I can always assume this to be true. This means that the parameters that affect the distribution of x are disjoint from the parameters that influence the, whoops, this should be given xi, that influence the conditional distribution of y given x, right? And so our parameter vector now is just the concatenation of the two parameter vectors, right? So I can always make that assumption. And if I do it, well, if I then want to right? Maximize the log of that, put in max log there and there. Well, then I'll get equals maximize the log p of xi given theta x plus the log of p of yi given xi and theta y, right? And this max now, right, this max here was over theta, and this max is going to be over theta, which is both theta x and theta y, right? And I can separate that into two separate maxes, because theta x appears only in this term, theta y appears only in that term. So I can get max over theta x, the log p of xi given theta x, plus max over, theta y, the log of p of yi given xi and theta y, right? And so what I've done here is I've split this up into two separate maximizations that I can perform separately. And so this one here, right, this is the maximum conditional likelihood estimation. And then this here, well, I don't actually need to use it when I'm predicting, so I can just drop theta x. I can ignore it, right? And so what I've done now is I've shown you how to get maximum conditional likelihood as a special case of ordinary maximum likelihood. Does that make sense to everybody? So when in the end, I'm going to use this for classification. And if I have the conditional probability of y given x and theta y, right? So if I know the conditional probability of y given x, then I don't need to worry about what the probability of x is for classification, right? So, so basically what I've shown here is that if you want to justify maximum conditional likelihood, you can start from maximum likelihood, and then the recipe is just you choose a model in which the parameters that affect the distribution of x, the marginal distribution of x, are disjoint from the parameters that affect the conditional distribution of y given x, right? And so that's kind of nice because it's a nice simple way of getting two very different looking classifiers. Right? And so the first line is what I just said. But you can also now figure out some things about the relationship between these two types of classifiers just from looking at this, this derivation. Right? So in particular, in maximum likelihood estimation, I don't actually need to have theta x separate from theta y. So I can couple theta x and theta y. And so you can think of maximum likelihood estimation as putting additional constraints on your parameter vector compared to maximum conditional likelihood, right? And so you would think then that maximum likelihood might have higher bias, right? Because it's putting more constraints. It's using a smaller model class, but smaller variance because it's putting more constraints. You don't need as much data to figure out what your correct parameter vector is. And that is, in fact, what you tend to observe in practice. That, for example, logistic regression tends to have a higher bias than, have a logistic regression lower bias than naive Bayes, but a higher variance. You need more data to fit the logistic regression, right? And you can actually, right, so here, if I said that, these two parameter vectors were the same, I got ordinary maximum likelihood. If I let them be different, I got max conditional likelihood. You can also do a soft tie, right? You can put a prior that says, well, there's some set of parameters theta x, another set of parameters theta y, and they're somehow related according to some soft constraint, right? And if I do that, then I can sort of interpolate between generative and discriminative models, right? So it's not an either-or proposition. Okay. So as the number of training examples goes to infinity, right? So we can compare the answers that these two different methods get. And if the Bayes net that I showed at the beginning is right, in other words, if the x's really are conditionally independent given the y's, then naive Bayes and logistic regression have to get the same answer, right? Because we're maximizing, we're getting the same we're getting the Bayes optimal predictor out of both of them in the limit of infinite training examples. And so since it's the same answer, they have to agree eventually. But if the Bayes net is not right, then logistic regression has the minimum possible training error, right? We specifically optimized logistic regression to have the highest possible training likelihood. We know from, for example, VC theory that training error is going to approach testing error. And so logistic regression is going to do as well as possible on the test set, right? Which using this form of classifier, which is nice, right? And so in particular, naive Bayes doesn't have that guarantee, right? It's not specifically minimizing training error. And so while it could do as well as logistic regression, it might do worse in the limit of tons of training data. That make sense? Yeah.
Logistic regression is a linear classifier, and naive Bayes is not. Why?
No, naive Bayes leads to a linear classifier as well, right? Logistic regression and naive Bayes both have the same functional form for the classifier, right? This is the functional form, that the probability of y is 1/1 is a logistic function of this z, which is calculated from your training data. It's just that logistic regression and naive Bayes have different prescriptions for calculating the w's, right?
This holds for all types of naive Bayes, like Gaussian.
Let's see. So Gaussian naive Bayes with equal variance between the classes also still gives you a linear classifier. And so all of this discussion holds as well. I was talking specifically about discrete naive Bayes because that's the simplest case. But everything I said makes sense as well for if you assume Gaussian naive Bayes, where every xij has the same variance between the two classes, because that's what you need to derive the linear form of the classifier.
But consider if the two classes are two circles, it seems that the distinct boundaries are getting a circle.
You mean like concentric circles? Well, so if they have the same variance, then you're not going to do very well in classification, right? They'll be the same circle, and there will be no good decision boundary. If they have different variance, then that's what I'm explicitly excluding by saying that I've got equal variance between classes. Okay. You could probably go through a similar derivation for naive Bayes with unequal class variances, right? You could get the form of the classifier, you could optimize the conditional likelihood, and the same comparison would hold. It just wouldn't be a linear decision boundary anymore. All right. More questions? All right. So, oh, go ahead.
So, can you go back one step? So here is the maximum likelihood always places additional constraint on theta.
Maximum likelihood puts more constraints on theta. That's right.
So in like normal analogy, the like theta x, theta y normally like decoupled. It won't.
Right. So if you start with a model where there's one parameter, call it theta, right? You could rename that parameter vector to be theta y, and then add some additional parameters, theta x, that allow you to model the marginal distribution of x, right? And so in the conditional model, right, there's no coupling between those parameters, whereas in the original model, there was only the one parameter vector, and it had to do double duty. It had to explain the conditional distribution of x, sorry, the marginal distribution of x, as well as the conditional distribution of y given x, right? And so you can actually make the analogy even more suggestive by saying that it's two copies of the same parameter vector, one of which is allowed to model p of x and the other p of y given x, right? And you can actually, like, there's a way to modify your model so that it has that functional form. It's the same parameter vector for p of x and p of y given x. And then you can say, well, you just add the constraint that theta x equals theta y, and that gets you back and forth between the generative and discriminative model. The tech report that's cited here shows how to do that. But that's not actually a necessary thing to do, right? All you have to do is add parameters to decouple P of x from P of y given x. Okay. All right. So with a finite sample, the comparison gets a little bit less one-sided, right? So if you have an infinite sample, well, you're very happy, and also logistic regression is going to do at least as well as naive Bayes, so you don't even have to know about naive Bayes. But with a finite sample, the comparison gets a little bit more subtle, right? So you can show that Gaussian naive Bayes, for example, needs a number of training examples that's order of the log of the number of attributes, as long as you have at least a constant fraction of the attributes that are relevant to the classification problem. In other words, have non-zero weight. And I'm not going to go through the proof, but basically you can use Hufting's inequality to say that each weight for naive Bayes is going to converge to its correct value. You can do a union bound over weights to say that then all of the weights are going to converge to their correct values uniformly. And then the decision variable, right, which is, you know, the sum of the weight times the attribute, that's going to be bounded away from 0. And so the fact that the weights are converging uniformly to their correct values means that the decision is going to be converging to its correct value, right? So that's a very quick sketch of the proof. But if you go through the rates that go through all of these, basically you get the log k factor from Hufting plus the union bound. And other than that, there's no dependence on the number of attributes. Logistic regression, on the other hand, needs a number of training examples that's linear in the number of attributes. And you can figure that out, for example, by applying the VC bound that we did a few lectures ago. So the VC dimension of linear classifiers is linear in the number of attributes. And then the number of training examples you can work out is linear in the VC dimension. So what that means then is that Gaussian naive Bayes is converging really, really fast, but not necessarily to the best possible linear classifier, whereas logistic regression is converging slower to the best possible linear classifier, right? And so what that tells you is exactly what I said heuristically a few slides ago, that if you don't have much data, then you should go with the one that converges faster, even if it's not converging to the right answer, unless the independence assumption is so horribly bad that that badness outweighs the difference between log k and k. Right? That makes sense? All right, good. And so we can compare them on you know, some real data sets. And so these are taken from a paper by Andrew Ng and Michael Jordan that made this comparison. And these are on the standard UCI machine learning databases. And in all of these graphs, the dashed line is logistic regression, and the solid line is naive Bayes. And so on this one, you can see what's very much the typical behavior, right? Within 10 examples, you're essentially at the minimum possible error for naive Bayes, right? It converges beautifully quickly, but after you get to, you know, 50 or 60 examples, logistic regression starts to pull ahead because it's converging to the optimal linear separator, right? So this is like the poster child for the theory, right? It shows that in practice, the theory actually gives you the right answer. Here, it's slightly slower convergence. There was basically slightly higher variance in the estimates, but still the same general picture converges. For small data, naive Bayes wins. For big data, logistic regression wins. Here, right, you can see that the same thing is happening, except that we didn't have enough data in this data set for logistic regression to catch up and beat naive Bayes. But it looks, you know, I'd be willing to bet that if we kept getting more data, this line's slope would eventually overtake this one, right? And then the same thing here. It looks like here the independence assumption is pretty close to correct, right? Naive Bayes gets almost 0 error, and so logistic regression isn't going to beat it, at least not by much. And it's much slower because there are lots of attributes. All right, so that's the sort of practical version of the theory comparison, and it's always nice when the experiments match the theory. Right? That means you can submit the paper. All right, so that's the end of generative versus discriminative. Any questions before we move on to decision trees? All right, so decision trees are, in some sense, just another way to do classification, right? They solve exactly the same classification problem that we told you how to solve in at least half a dozen other ways throughout the rest of the class, but they have some unique features that make them interesting to look at. So what is a decision tree? First of all, machine learning can't claim credit for inventing decision trees. They existed long before anybody had even thought of, even before Babbage had thought of his difference engine or his analytic engine, right? And so if you go on the web now and you search for Dichotomous classifier, which was the name before machine learning people got to it, you'll get a bunch of examples of ways that people used to do, for example, field identification of insect species, right? And so, the way this works is you go and you look at your insect and you say, okay, does it have one pair of wings or two pair of wings, right? If it has one pair, it's order Diptera, which is Greek for two wings, as opposed to four. And you go to the classifier. This is a link that goes to the page where you start classifying Diptera. Whereas if it has two pair, you go to question number 2, right? So it's like a series of yes/no questions that you answer. Each one tells you where else to go, and in the end, you get a classification, right? This is, let's say, a praying mantis or a daddy longlegs, right? Or maybe some new insect species that you've just discovered. And you also see them in, for example, geology. I've seen them used for field identification of rock types. But in general, you have a classification problem with a bunch of x-y pairs. Each x has k features. Each y is binary, right? And you wind up getting a classifier that looks like this, right? You start off by saying, well, is x3 greater than or equal to 7, question mark, right? And so you'll have a node for that question. And if it's no, you go that way. And if it's yes, you go that way, right? And then you have another question here. Is x2 less than or equal to 5, right? And no and yes, right? And then maybe, x4 is binary, right? So is x4 true? Well, then no and yes, right? And then at the leaves, you have some kind of prediction, right? So you'll predict y, p of y is equal to 0.3, right? If this is a classification problem, or p of y is equal to 0.9 in that branch, right? So everybody understand the form of the classifier? Good. So usually these are just yes/no questions in the true/false questions in the nodes, but you could have other types of question as well, right? You could have a multiple choice question. It's not a decision tree unless it's a discrete answer, but the answer can be multiple choice as opposed to binary, in which case you just have, D children if there are D answers. The other thing is that if you have, you could, if you wanted to, have yi be a real number, right? In which case you'd have something like, yi is equal to 7 here, right? And that would be a prediction about the expectation of yi, right? So, and then the other thing I wanted to mention is that if you have just one level, right, so if you just ask the first question and then all of the children of the root are just leaves, that's called a decision stump, which is, for small decision tree, or what's left of a decision tree after you cut off all of the leaves. And so the typical picture of what the classifier looks like, right, you have R2, which is represented by the slides, and you'll have a split on the x variable, right, and then a split on the, inside that split, right, you'll have a split on the y variable, and you might have a different split on the y variable here, right, and then in here you might split the x variable, and you could split the x variable twice, right, at different thresholds, and you get this nice rectilinear division of the plane. right? And so the whole thing, right, decision trees were actually invented by Pete Mondrian, right? Or not. So there's a ton of variants of decision trees, right? So you could have different kinds of questions at the internal nodes. The most common is, height greater than or equal to 5, right? Like just a binary question. But you could also have multiple choice, right? Right. It could be red, green, or blue, and split those 3 ways. You could also put in a logical function like height greater than or equal to 5 and color equals blue, right? Or XOR or whatever. You could also use a linear threshold function, 3 times height, plus width is greater than or equal to 2, right? So you could have all of these different types. You could have different types of labels at the leaf node. The most common is a constant, right? Like 3 or true, or p of true equals 0.5, right? But you could also have any, you could put linear regressions in the leaves, right? Any of the classifiers or regressors that we've used, they can go in the leaves of a decision tree, right? The other thing you can do is you can label the internal nodes, right? So you can have a decision tree that looks like that, right? Or you can label the internal edges, right? And so you could have, 2, 4, -2, 5, right? And what this means is that, well, if you get here, right, the prediction is 2. If you get here, the prediction is 4 minus 2 is 2, right? Whereas if you get here, the prediction is 4 plus 5 is 9, right? And you could use sum to combine them, or you could use any, max multiplication, right? Bunch of different ways to combine them. You can also have different forms, right? So I said decision tree, but you could have a decision list, which is basically just a caterpillar-shaped decision tree, where the branch is always, right, one child is a leaf and the other one keeps going until finally both children are a leaf. Or you could have a decision diagram, right, where you have something like that, and 2 things lead to the same node like that. And I don't know, maybe this one goes over here too, right? If you were to allow side effects and cycles, you'd get all the way up to a flow chart, but that's not usually considered a variant of a decision tree. But the limiting case is this, right? I don't know if you've ever done the Choose Your Own Adventure books, but that's where you have basically a page of text that gives you the question that you're supposed to answer, right? And then you turn to the next page to keep going. Disclaimer, I think some of these books have cycles in them, so they might not be valid as decision DAGs, but whatever. And then in the end, you find out whether you collect the treasure or get some grisly death, right? That's usually the way it works is that 9 of the endings are grisly death, and only the 10th that is very hard to find is the good one. All right. So to do it on actual data, right? This is a famous data set. This is the Fisher iris data, where you have 3 different types of iris that have actually 4 attributes, but I've plotted 2 of them here, right? And you could do a decision tree where you split first here, right? And then let's say we split here, right? And then maybe we could split, here and here, right? And get different, this is definitely red, right? Red here, this is green, definitely blue in here, definitely green in here, and here it looks like there's no way to split further to increase accuracy very much, right? And so that would be an example of what a decision tree looked like on some real data. Okay. So decision trees are nice because they can represent a lot, right? So if I have you know, a binary, a Boolean function like and, right, I can do a split like this and a split like that, and I've got 3 pure classes, right? Each one of these leaves of the decision tree is pure, right? Same thing for, you know, or is almost the same thing, right? Like that and like that. XOR even, right? So plus, minus, minus, plus. Well, you can split like that and like that, right? And so you can represent a lot with a decision tree. As a matter of fact, you can represent any piecewise constant function where the pieces are on squares, and that class is actually dense in the space of all measurable functions. So you can represent a lot with a decision tree. Of course, the flip side is that once you start getting very complicated functions, it starts getting to be really big decision trees, lots of splits, right? And you need a lot of data to learn them. So pros and cons, a decision tree, the pros is that it's pretty flexible. It works pretty well. Another nice thing that we haven't talked about is interpretability, right? So people often use decision trees because when you go back through, it's like, you know, a bunch of easily understandable yes/no questions, right? And they lead you inexorably to a leaf that tells you what the answer is. And presumably, by the time you get to a leaf, it's fairly pure. And so, you know, people will believe you when you say, well, if you ask these questions, it separates off a set of the training set that's, let's say, relatively purely class 1, and that's a good reason for you to believe that this new example is class 1, right? So people will actually believe you if you hand them a decision tree. They won't necessarily so much if you hand them a support vector machine, right? The reproducing kernel Hilbert space came and said that the answer is 4, right? And, you know, okay, fine, right? The other nice thing about decision trees is they're really fast at test time, right? So you just ask a bunch of simple questions and you're done, compared to, let's say, support vector machines where you have to compute kernel to each one of your support vector, which could be thousands or millions. And another actual nice pro is that decision trees are closed under common operations like addition, subtraction, multiplication, right? So basically all you have to do, it's easiest to see with decision diagrams, right? So let's say I had a decision diagram which had, you know, 3, 2, minus 1, 4, right? And so, you know, and here you got 5 and 7, right? Well, and then another decision diagram, let's make it a really simple one, right, which I just add 6 to my solution, right? And if I want to add these two things together, well, all I do is I make these arrows all point here, right? And so these two things are added. And it was really easy, right? But you can do it, you can actually do it by, for example, taking the cross product of all of the leaves of 2 decision trees to get a decision tree that represents the sum or the product of the 2 functions, right? So those are a whole bunch of pros that are, you know, somewhat unique to at least the, you know, these guys, interpretable, fast, and closed under common operations, are pretty much unique to decision trees. Now, of course, there are cons. So I haven't shown you the learning algorithm yet, but unfortunately, learning is NP hard. It's not so good when you have to solve an NP hard optimization problem to get your classifier. And they're often slightly below state of the art in classification performance, right? So they're good, but not as good as some more modern classifiers. However, there are ways to improve the performance of decision trees, which we'll get to later in the lecture. However, those get rid of the interpretability. So, you know, often you're stuck with a slightly lower performance if you want to get the interpretable benefit of decision trees. Yeah?
So how do you actually train the trees?
Let's see if that's the next, yeah, there. I'll pay you after class. So learning, right? Learning is going to be by maximum likelihood estimation. So what we're going to do is we're going to try and find the tree that performs as well as possible on our training data, right? And so let's, here, because this is a small set, we can actually just do this by inspection, right? So let's start by looking, well, okay, the simplest decision tree is no tree, right? So we just say, okay, no tree, and the best maximum likelihood prediction is that P of plus is equal to 2/5, right? So that has likelihood, well, there's going to be, I'll sum the log probability over the training data. For all of the minuses, we'll get log of 0.6, and there are 3 of them, plus 2 log of 0.4, right? And that's going to be our log likelihood. For concreteness, let's say this is log 2, because that'll be useful later. Okay, now let's consider the decision tree where we have just one node. Is it red, right? And so we split no and yes. If it's not red, well, then we have 1 minus and 1 plus here. So the maximum likelihood estimate is going to be P equals 0.5, right? And here we have, if it's red, there's 2 minuses and a plus. So P is equal to 0.333, right? So the likelihood of this thing is going to be, well, these guys are both going to get log of 1/2, right? So that's 2 log of 0.5 plus, and then here we're going to get two things that are good, 2 log of 0.667, right, plus log of 0.333, right? So that's going to be the likelihood there, right? And then there's another one-node decision tree, which is it fuzzy? And so no and yes. For no, right, we get plus, minus, and plus. And for yes, we get 2 minuses, right? And so here the probability is predicted to be 0, and here the probability is 2/3, right? And so here, if we write out the log likelihood, we get 2 log 1, right? Which is log 1 is 0, so this just gets nothing. And then here we get log of well, so for the minus, we get log of 0.333, and then we get plus 2 log of 0.667, right? And so this one is better than this one, right? Because you can match the log here, and then you have a negative term here in this one, right? So this has lower likelihood than this does, right? But we can actually do even better, right, by splitting here on, if we split here on fuzzy, sorry, if we split there not on fuzzy but on red, right? So of the non-fuzzies, right? So those falses, there's one. So if we get non-red, right, and not fuzzy, that gets us this guy, just 1 plus. And if we get red and not fuzzy, that gets us a plus and a minus, right? And so this one's going to be even better because it's split off 1 into a pure class and left here. And then we can't do any better, right? There are no more attributes left to split on. And so this is going to be the best decision tree here, where we split first on fuzzy and then on red if fuzzy turns out to be false, right? So you guys should all know now how to build a decision tree by enumeration, right? Which is not the best algorithm, but at least it shows you sort of the way to learn them. Is that right? Yeah, that's right. So with bigger data sets and more attributes, you have to use a heuristic search, right? And there's a bunch of different heuristic searches that people proposed, but the one that seems to work best is to build it greedily top down, right? So you start with all of your training examples in a single bin, and then the prediction for that bin is going to be the average of all of those training examples, all of their y's, and then you repeat. you pick, right, repeat comes back up to here. You pick an impure bin, right, a bin where there's some variation in the y's, and you try some candidate splits. For example, you could try all single attribute binary tests, and you pick the one that gives you the largest increase in likelihood out of your set of candidate splits, and you make that split, right, which winds up adding a node to your decision tree and splitting your examples into 2 sub-bins. And then you keep repeating until either all bins are pure or there are no possible splits left, right? In other words, you're down at, you've split on all of the attributes to get to some leaf. That leaf still isn't pure, but you have to stop anyway, right? So it's a really simple algorithm, but this actually seems to work pretty well. So questions on the algorithm? Yeah.
Doing the same thing as maximizing the accuracy in this case? Is the same?
Likelihood and accuracy are not exactly the same, but they're pretty highly correlated, right? Accuracy is a discrete measure, right? So it's going to be an integer between 0 and the number of examples that you have, whereas likelihood's going to be a real number. And you can think of likelihood as being the sort of partial credit version of accuracy, right? So if you if you predict 0.7, then you get partial credit for getting the things that are plus, and less partial credit for getting the things that are minus, right? So it's basically a confidence-rated version of accuracy. More questions? All right. So this maximum likelihood training, using it to select splits, there's a name for it. It's called information gain. And so I've got here, right, this is what I wrote on the previous slide. If we split on red versus splitting on fuzzy from the initial bin, right? So here, if we work this out, this turns out to be minus 4.85 bits was our initial likelihood. If we split on red, it turned out that we got minus 4.75, right? And so gain was 0.1 bit. Right? And here, if we split on fuzzy, we got minus 2.75, right? And so our gain was 2.1 bits, right? And so we'd select to split on fuzzy instead of splitting on red, right? And so this improvement in the likelihood is called information gain because of the sort of information theoretic interpretation of how many bits would I have to give you to code the rest of the data set, to code all of the y's given the x's. And in general, information gain, this is the expression, right? The entropy of the label minus the entropy of the label given the thing you're splitting on, right? This is the information gain of y given x. And here, because x, the thing you're splitting on, is a random variable, you have to take the expected entropy for both of the possible outcomes of the thing you're splitting on. Right? But what it turns out here is that it's exactly this, right? You get the, that's the expression for it. It's the improvement in log likelihood. All right? So you'll often hear information gain in the context of splitting of decision trees, but what it really means is maximum conditional likelihood. Right? So I've told you now so far about binary attribute decision trees and mentioned real-valued attributes. So with real-valued attributes, typically what people will do is pick one split on the real-valued attribute to make the binary test in a node of the decision tree. And heuristically, what you would think is, right, if I put the split here, right, then it's going to have pure blue on that side, right? But it'll have about 50-50 blue and green on this side, right? So that's going to be really good for this bin, but not so good on that bin, right? On the other hand, if I split about here, it would be, pure green on that side and about 50-50 here, right? Whereas if I split in the middle, right, I would get that'll be the optimal split, right? It'll give me the most information about whether it's green or blue. Right, so what I'm showing you here is I've sorted all of the blues and all of the greens along the x-axis, and I'm showing you the cumulative count, right, scaled to be between 0 and 1 of all of the blues and all of the greens. Right, so the model here was there were two normal distributions, one here and one here. I sampled a bunch of blues from one, a bunch of greens from the other. There is an overlap, right? And so the best split is going to be somewhere in the middle. That make sense to everybody? All right. And algorithmically, if you want to do this, right, there are infinitely many splits, but you're only ever going to actually care about the splits, right? There are only finitely many different partitions, right? And so what you can do is you can sort all of your data together, enumerate all of the partitions, right? So just go through all of the data points one by one, and suppose that I split between this data point and the next one. Right? And then you can accumulate how many blues and greens are on each side of the split and calculate the information gain for each split in n log n time. Right? You go through n log n to sort and then linear to just scan through and pick the best decision boundary. Okay? So building on a continuous attributes is not actually any harder than building on discrete attributes. You can also do multi-way discrete splits, right? So here's a very highly realistic medical database, right? For every patient, I've got their social security number, their temperature, and a binary variable whether they're sick or not, right? And so from these, I want to classify, are they sick? And so if I split on their temperature, I get two fairly pure leaves, right? One minus minus and one that's plus plus and minus. But if I split on social security number, I get 5 perfectly pure leaves, right? And so if I just use information gain, I'm going to pick to split on social security number, which seems like probably the wrong thing to do because I'm unlikely to generalize to a new patient. And so basically, this is just pointing out that what you need to do is penalize splits that shatter your data set into a larger number of pieces. And there are a bunch of different ways to do that, all of which have more or less heuristic justifications. Things like just have a penalty based on the number of splits that I have, or I could use some kind of a statistical test to see whether there's a significant association between the split variable and the thing I'm trying to predict, right? So there's a bunch of different ways. I'm not sure I can recommend one is better than any of the others, just to know that not having any way to penalize is always going to be a bad thing, right? And then the different ways to penalize, there are some situations in which each one works best. Okay? So even with tests for the significance of splits, often when you build a decision tree, you'll wind up overfitting your training data. And so what you could do is you could try early stopping, right? You could try just building your decision tree out to a certain point and then stopping. But what actually seems to work better is what's called pruning your decision tree. Again, a botanical metaphor. So what you do is you grow your decision tree on your training set with no care for when to stop. You just keep splitting it out until you can split no more, right? And then you take a holdout set and you use the holdout set for pruning. And what the pruning is, you take a decision tree that looks like this, right? So this is our rusty robot, right? We check whether he's going to be rusty by first checking whether he's metal, rainy, and outside. And I've added a purple attribute, which doesn't seem to be relevant. And what you can do is just consider, take this and just get rid of it. And that means that for the no branch of outside, you would predict, well, let's say that these were, even counts, and so you'd predict, let's say, 0.2 on that branch, right? And so then you could consider, since outside is now the final node along a path from root to leaves, you could consider removing the outside node and collapsing it up to just be a prediction when you have rainy yes, right? And so you can just keep doing this. And what you do is greedily from the leaves towards the root, consider removing each node in turn. And then once a node's children are all removed, it itself becomes eligible to be removed. And then you stop when the holdout error stops decreasing, right? And so typically the first few prunings will help a lot with holdout error, and then at some point you'll reach a diminishing returns where your decision tree actually helps with holdout error rather than hurting it. Okay. So the typical decision tree training algorithm is, you use information gain or some other splitting criteria. There are a lot, but information gain is a pretty good one. You split your decision tree all the way out as far as you can on your training set. You prune it back on your holdout set, and then you're done. And there's a bunch of different pieces of software you can use. Again, we recommend downloading software off of the net rather than implementing it yourself. The famous ones include CART, which stands for Classification and Regression Trees, ID3, I forget what that stands for, C4.5, J48, right? There's a bunch of these things. You can just download one of them off of the net and apply it to your data, and so it's actually quite easy to do. There's one trick that's in several of these pieces of software that's actually kind of useful for interpretability, which is pruning as rules. So what does that mean? I can take each leaf of my decision tree and convert it to a rule, right? So this leaf here is metal and not rainy, right? This leaf here is metal, rainy, outside, and not purple, right? So I can convert each leaf to a rule, and then the prediction of that rule is whatever was in the leaf. And then I can prune as a rule, which means that I can consider dropping any of the tests from the rule, which is kind of nice, right? Because it means that I don't have to drop leaves first, right? If I happen to make a bad split early on in my growing process, but then fix it later, then I can just get rid of that split in the rules, and it won't make a difference, right? And so there you might get to a situation where two or more rules might both apply to a test case, and then you combine them using something like averaging. Okay. And so this is nice both because it actually helps performance, and also because it results in something that's even more interpretable, right? So because it lets you prune more aggressively, you can prune things that were, you can prune bad decisions you made early in the splitting process. You'll typically get a smaller classifier out in the end, and a classifier that's basically a bunch of case analysis. Here's a bunch of rules. You just go through and you see which rules apply to your data point. People really like looking at that, and they can convince themselves that that's a reasonable classifier to use. All right. So questions about decision trees before we move on to the yes. Will there be any problem if there's dependence between the variables? Right, so if there's a lot of dependence between the variables, what you can do is just split on one of them and ignore the other, right, if they're perfectly correlated, right? Then what will happen is that if you don't know in advance which ones are correlated, your decision tree learning algorithm will do that for you, right? So split on one will have essentially the same effect as a split on the other, and so it'll just randomly pick based on some noise in your training data, right? So decision trees are actually pretty robust to having correlated attributes. Basically, what they wind up doing is they wind up essentially ignoring the attributes that don't matter. They'll split on them only at the end when there's essentially noise left. More questions about decision trees? All right, so there's one last trick for decision trees, which is pretty important, which is called bagging. It's short for bootstrap aggregating. So it's a nice little portmanteau word. You can use it with any classifier, but it turns out that if you use it with decision trees, it's actually a pretty good classifier, right? So what it is basically you have your training set, and you generate a whole bunch of bootstrap resamples, right? The same way we told you about before, independently, pick with replacement from your set to make a new bootstrap resample. And then you train a decision tree on each one of these bootstrap resamplers, and then in the end you vote all of these decision trees that you got, right? So the idea is that the bootstrap is going to give you, it'll preserve the signal, but it'll sort of change the noise. And so when you do M bootstrap resamples, the decisions you make due to the noise in the training set will be different on all of them, and so they'll average out, whereas the decisions you make due to the signal will get preserved, and they'll be the same on each one, and so they won't average out, right? And so voting, for example, means that if tree 1 says 0.7 and tree 2 says 0.9, and if we just had the two trees, we'd predict 0.8. Okay? Yeah. Not a question? Okay. Any questions? Okay, so this is nice, and it's a really simple thing that you can do. This train a decision tree on each one. You have a bunch of choices for what you do. So the most typical thing to do, the thing that people tend to recommend, is first of all, don't prune. Right? So the idea is that the bootstrapping is going to handle the noise reduction for you, so you don't need to prune. You just keep all of the information from that bootstrap resample. But the other thing is the more variability you can get in your decision trees, sort of the more variety, the more you kick your local optimizer out of its local optima. And so the better a chance you have of getting a good answer overall. And so what people will do is they will you'll restrict to k prime attributes where k prime, is much less than the original number of attributes k, right? And you'll do that by selecting just uniformly at random a bag of k prime attributes for each decision tree. And so the idea is that each decision tree is going to try and focus on learning in a different part of the attribute space. With high probability, you'll wind up, especially if there's only a few attributes that are mostly relevant, with high probability, you'll get a lot of trees that contain those attributes. And it's easier to build a decision tree on fewer attributes, and so the local optima won't be as much of a problem, right? And with these choices, bagged decision trees are called random forests, which is a trademark, but I'm using it for fair use right now. And these are supposed to be pretty close to the state-of-the-art classifier, right? So they perform noticeably better than plain decision trees in terms of classification accuracy, but they're a little bit less interpretable because instead of just having a small set of rules, you have 1,000 different sets of rules and you're averaging over them, right? So you're trading off interpretability against performance. Questions about bagging? Yeah.
The probability response to probability at the lead.
Mm-hmm.
It's basically a mix, which is why the probability.
So the probability at the leaf of a decision tree is basically you count the number of pluses and minuses at that leaf, right? And then so for each one of these decision trees, you'll get different leaf probabilities because you have different splits because you have a random process in building the training data. So they'll all make slightly different predictions. If you are in a region where it's clear that you're in class 1, then all of your decision trees will be predicting class 1. If you're in a region where it's clear that it's class 2, everybody class 2. If you're in the middle, some of your decision trees will get different splits and they'll all get slightly different boundaries, right? Why is bagging particularly useful for decision trees? Probably, I guess I would say because of the local optima. In other words, your decision tree procedure is going to have trouble getting to the global optimum, but in some sense, it's not that hard an optimization problem. Like some of the splits should be obvious. And so if you just perturb your training set a bunch of times, you're likely to get some examples where you do well. Right? These axis parallel splits, they have trouble doing things like diagonal decision boundaries. And so if a diagonal decision boundary happens to be the case, then the more decision trees you average together, the easier it's going to get to be to approximate a diagonal or a circular or an elliptical decision boundary. Right? So basically, going to voted decision trees gets rid of some of the bias of the decision tree class, the class of small decision trees. And so that's another reason why bagging helps decision trees a lot compared to other classifiers. The other reason actually is that each decision tree is very fast to apply. And so if you bagged, for example, support vector machines, where each support vector machine got you 1,000 support vectors and you had 1,000 of them, right, you'd still have something that would be kind of bad to apply on your test set. So there's a bunch of reasons why bagging happens to work particularly well with decision trees. More questions on bagging? Yeah.
So how do you restrict the attributes so you select?
Select at random.
How do you know if the ones that you selected are
You don't know whether they're the important ones, but hopefully the idea is that as long as there's a decent number of important ones and you don't select too horribly badly, too horribly few, there'll be a lot of decision trees that actually do get the right attributes in them to be built. Oh yeah, right. You select a different set, just like you have a different bootstrap resample for each tree. You have a different set of random attributes for each tree. That's, yeah, good point. Right. If you selected a single bad set of attributes and committed to that, performance would be pretty horrible. More bagging questions. All right. Cool. So we have one more thing about bagging. It gives you a nice way to get error estimates. So on your homework, you guys did straight application of Bootstrap to estimating error, and it seemed kind of optimistic, right? Because you're training and testing on the same example if it happens to show up in both splits. But what you can say is that, well, for each bag, it's only going to contain about 2/3 of the examples on average, right? And so you can use all of those out-of-bag examples to estimate the error rate of each tree. And then you can also estimate the error rate of the overall vote by, for every example, classifying it using all of the trees for which it is an out-of-bag example and voting over all of those trees, right? And so each of those is going to be an unbiased estimate of the error rate of a vote of about 2/3 of your classifiers, right? And so it's going to be conservative because you're only averaging over about 2/3 of your tree, but that conservatism is actually a good thing, and it's also pretty small. And for the rest of it, it's subject to the bootstrapping being valid. It's going to be a good error estimate, right? So it gives you a nice way to estimate the error of your hypothesis as well. All right. So now we have 10 minutes to talk about boosting, which is not going to be enough. We'll continue boosting at the beginning of next lecture. So boosting is also one of these things where you can use it with any classifier, but it works particularly well with decision trees, which is why we're covering it in the same lecture. So with bagging, we introduced the idea of a voting classifier, right? So we had our original classifiers, which were functions from, let's say, just a plain classifier, a function from RK to just -1 and 1. And then a voted classifier would be you'd take the sum of a whole bunch of classifiers and you'd test whether it was positive or negative, right? And you could normalize, right? But that doesn't change whether it's above the threshold of 0 or not. And then, of course, you could have a weighted vote where each classifier gets a different weight. And we can assume without loss of generality that all of the weights are positive because we can assume that for every, for example, decision tree that gives you one set of predictions, there's another decision tree where you get the exact negative of all of your predictions, right? You just swap the class labels on all of the leaves. So we can assume that instead of taking the one with a negative weight, we'll take the one with a positive weight and put that into our vote. And of course, we can scale so that the alphas all sum to 1, but that doesn't actually matter, right, because the threshold is 0. Okay? So voted classifiers are kind of nice. They actually increase the expressiveness of your hypothesis space. So what I've put here are 5 different linear separators. And I've counted for each region how many of the linear separators say yes and how many don't, right? And so the orientation is such that in this middle pentagon here, they all say yes. If we cross one of them, we get 4, then 3, and then 2 if we keep crossing them, right? And then you never get below 2 of them saying yes because they're pointing in enough different directions, right? And so if I vote on this, I could, for example, get this 5-pointed star here, right? Which I definitely couldn't have gotten with a linear classifier, right? Or I could get this other weirder shaped region. So that just sort of, shows you that if I get enough different classifiers in my vote, I can get a sort of much more expressive hypothesis class. And so what we're going to do now is use this maximum conditional likelihood idea again. What we're going to try and do is learn a voted classifier by maximum conditional likelihood. And given this functional form, we hope to get a really good classifier out in the end. And of course, the problem is going to be that if we do this maximizing likelihood over this very flexible hypothesis class, we do have to worry about overfitting. But it turns out that there are ways that we can avoid it. And so that's basically what boosting is. It's trying to learn a voted classifier by maximum conditional likelihood, or by some other similar training criterion. All right? And so the benefit, of course, is that because it's a bigger hypothesis class, we can hope to get much better performance. Again, only if we can do overfitting, avoid overfitting, right? And so here are a couple of examples of how the hypothesis class is extended, right? This is an example of some voted axis parallel splits that are approximating a diagonal line. And then this, of course, from the previous slide. So what does that look like? Right, so if we take our voted classifiers and enter the matrix, right, what it looks like is this. We have n different training examples. And then one classifier, let's say classifier number 1, it'll get the first training example right, the second one right, the third one wrong, and so forth, right? And the second classifier will have a different pattern, right, and so forth. And then, right, these are going to be x1, x2, and so forth, right? And this is this one says that classifier 2 gets example 4 wrong, right? So we can make a matrix like this, and because there are n different training points, there's going to be at most 2 to the n distinct classifiers in our hypothesis class. There could be fewer, right, because of the VC dimension argument that we covered a few weeks ago. But at most, there's going to be 2 to the n. So this is going to be sort of a big, wide matrix, right? It's going to be n by up to 2 to the n, right? And so what we're going to do with voting, right, is we're going to try and come up with weights on each of these classifiers, right? Alpha 1, alpha 2, alpha 3, and so forth on each of the classifiers. And then we're going to take a linear combination of these columns, right, with weights alpha, and that's going to be our final classifier, right? And the final classifier, if the weight of the plus ones is bigger than the weight of the minus ones, right? In other words, if the weighted vote, more classifiers tend to get it right, then this will be a positive number here when we take our linear combination. And so if most of our classifiers get it right and we take our linear combination, then we'll get this example right? And then the same thing for each of the other examples. So what we're trying to do is come up with a bunch of weights so that when we take that linear combination of the columns, we get an all positive vector out on the side, right? So that's just a matrix multiplication. We take this matrix, call it z, we multiply it by alpha, and what we want is z times alpha is greater than 0. Right? And so that's an optimization that we can try to solve. So let's just write that down, right? So if we write si is equal to the label on example I times our vote, right? Then the voted classifier is going to be right if and only if this weighted vote is, the total vote is bigger than or equal to 0. We can write this out as yi times our vote, which is the sum over all classifiers j of alpha j fj of xi, right? And so we can also write this in terms of our matrix before, right? This is sum over j of alpha j times zi j, right? That's the matrix multiplication that I said before, right? And so this gets our the correctness of our weighted vote as a function of the alphas. That make sense to everybody? Yes? All right, and so what we want is to maximize likelihood, right? So the maximum conditional likelihood estimate. What we want to do is minimize over all of our alphas, and also we'll call S a variable as well, the sum over j of h of sj, right, where h of sj was again this function, right, that told us what the log likelihood was for each example, right, subject to the constraint that S is equal to z times alpha, right? So this is z alpha. Okay, so does that make sense, right? So what I'm doing, the objective there is the log of the conditional likelihood, and the constraint just says that I have to correctly identify the weighted vote for each one of my examples. All right. I can't tell whether people are quiet because this is obvious, because it's boring, or because it's confusing. So Z here, Z is this big matrix here, so this, we'll call it Z, right? It's the matrix of, for each training example and each classifier, does that classifier get the training example right or wrong, right? And so what I showed here on this slide pictorially is that if I multiply this matrix Z by a vector alpha, right, so this is left multiplication by the vector alpha, what I get out on this side is for each example, the weighted vote on that example multiplied by its label. Right? And so that's going to be positive if and only if the weighted vote gets the correct label. Right? And then if I say that the probability is going to be a sigmoid function of the weighted vote, right? That's one way to turn this into a maximum likelihood problem. Then I get that the log likelihood is this function applied to the weighted vote, to the signed weighted vote. And so I want to maximize the likelihood, or min the negative log likelihood, subject to the weighted vote being correctly calculated, right? Or I could write it the same way, min over alpha, sum over j of h of z alpha's jth component, right? That's maybe a little bit more confusing notation, but it's more compact. The training data will be used a very large number of times, right? So this is the same training data on every single one of these T distinct classifiers.
So you first use training data to train the classifier?
So here I'm not training a classifier at all. I'm just enumerating all of the possible ones. I know that there are fewer than 2 to the n, so this is a bad algorithm, but I could just write them all out and get this big matrix Z, right? So I'm using the training data to construct this matrix Z. And in particular, I'm using the training data once for each column of this matrix, right? So I'm using it as many as 2 to the n times. So you can see why overfitting might be a risk, right? But we'll get to that later when we talk more about boosting. All right. So this optimization problem, I'm not going to talk about how to solve it today because we're almost out of time. But I just want to make sure that the optimization problem is clear because we're going to be spending a bunch of time with it at the beginning of next lecture. All right, cool. So more boosting on Wednesday. The other thing, just a reminder, your faculty course evaluations are due. This is the first time I've taught this course, so I'm particularly interested to see feedback about things that we can, well, hopefully things that I did perfectly, but also things that we could do better. And so, you know, please do fill those out. We definitely look at the answers, and it's important to us to see them. All right, see you guys on Wednesday. Have a good rest of your week. Oh, and also at the poster session tomorrow. Don't forget about that.